In this video, I'm going to discuss the different parts of the X-ray tube, and we'll start with kind of the overall parts. These little boxes. You've got the cathode end, which is negative, and that's going to be the part over here with the filament. And then you have the anode end, which is positive, and that's going to be over on the opposite side with that slant diagonal face. Okay, so on the cathode end, we're going to discuss that first. So on the cathode end, the biggest part that you have that we'll talk about is the filament. And the filament, when you press the button, will be heated and it will glow red hot. It will give off incandescence, which is incandescent light or incandescent heat. Just means that it's glowing red hot. And that filament, once it's heated, boils off electrons. Instead of creating light or heat, it's designed to create electrons, and they form in an electron cloud right around that filament. The other part that's over here on the cathode end is your focusing cup. Wait a little more. So the electronic focusing cup is just this little bowl-shaped piece here. And what it does is it helps to kind of focus those electrons in just a minute. But right now it's kind of helping to hold that electron cloud together. So those are all of the parts of the cathode end. And I tell the students the easy way to remember the cathode and that the cathode end is negative is if you think about cats, the C-A-T at the beginning of cathode. Cats with curly tails, like your filament, are bad. So there's your negative. So cats with curly tails are bad, and that gives you your cathode end of the machine has the filament and that it's negative. Okay, we're going to cover this up for a second. And we're going to go over to the anode end. So this is the opposite end. So you have your electron cloud, you have your filaments here. Once that electron cloud is formed, then your anode and your cathode are going to become activated. And what that means is up until this point, the cathode's kind of been neutral. It didn't really have a charge yet. But once that activates, that cathode becomes negative and the anode end becomes positive. Well, electrons, negatively charged, cannot stay in the cathode end once it becomes negative. They're going to be pushed away because like charges repel. But opposite charges attract. So your electrons here, which are negative, get pushed out of the focusing cup at the cathode end because it became negative, but they're also being pulled across to the anode end because it became positive. Okay? As they travel across, as the electrons travel across, that's called the cathode stream. They're leaving the cathode, headed toward the anode in the cathode stream. Okay, the first piece that they will interact with is the focal spot on the tungsten target. So this whole square is your tungsten target, and the center of it is your focal spot. And that just means where the focusing cup is directing the electrons to hit. So the electrons hit the focal spot of the tungsten target, and X-rays exit. Okay, and they're allowed to exit through this tube window, which is not lead. Okay, the rest of the envelope, that glass envelope, the rest of it is leaded glass, and lead is something that would block or attenuate X-rays. So if the glass envelope, which is leaded glass, is stopping the X-rays from passing through, the only place that they can pass through is this tube window, which is made of unleaded glass. That's all these little arrows are indicating. X-rays can go in different directions, but they can only exit through that window where we want them to. Now, the process of making X-rays is not very efficient, but it is consistent, and we like consistency that allows us to control it and make it as safe as possible to use with our patients. So, while these X-rays are being made from the electrons colliding, only 1% of the energy transfer that happens with that collision, only 1% is made into X-rays. The rest of the 99% becomes heat. When that happens, that heat has to be dissipated. So it travels out the copper stem, because copper is a really good conductor, and all of the materials that are used in the X-ray machine are really specifically put in there for a reason, and copper is just an example of that. Copper is a good conductor, and it will help dissipate the heat. So the copper stem is going to pull the heat away, and the next piece over here is called the radiator. It's a radiator just like your car has. Your car has a radiator to help dissipate the heat, and that's the same thing that's happening here. I did uncover the word vacuum. Part of what makes this machine so consistent and makes the design so consistent is that all of the air has been sucked out of the glass envelope, out of the X-ray tube, to create a vacuum. And what that means is there are no particles inside that tube for the electrons or the X-rays to bounce off of. So their only way to travel is in the direction that they are designed to go. They aren't going to be bouncing off of other things, or they're not interacting with anything else inside that glass tube, and they keep it as pure as possible by creating that vacuum. I didn't explain the parts and what they're made of and the other pieces, so let me go back and do that. Let's uncover everything now. The filament itself is made out of tungsten steel, and that's the same thing that your tungsten target is made out of. Tungsten steel is just a very hard steel that is very resistant to all of the use and abuse that the X-ray tube is going to throw at it. So those are all of the different parts of the dental X-ray tube. I did want to throw just a little more information in there to kind of finish this process out. Once the X-rays exit, or as they are exiting the window, that useful beam of X-rays is also called the primary beam or the central ray. So you'll see central ray and primary beam kind of used interchangeably. And once they pass through that window, they will go through an aluminum filter. Again, aluminum was chosen on purpose because aluminum is a soft enough metal that the X-rays that are strong and at the setting that we want them to be, they will be able to pass through the aluminum, but weaker X-rays will be blocked. So we don't want the weaker ones because they're going to be absorbed and they're not going to give us a diagnostic use. However, the stronger ones will penetrate through the tissue, through the surfaces, and get to the film or the sensor to create the image that we want. With aluminum filters, and this is in your textbook as well, but with the aluminum filters, the thickness of the filter is determined by the kVp setting or strength of the machine. The rule is that it's 1.5 millimeters of aluminum filter if your machine operates below 70 kVp. If your machine operates at 70 kVp or above, you would need 2.5 millimeters of aluminum filter. Okay, so that's the aluminum filter. The next step is that the X-ray beam or the primary beam is going to pass through the collimator. We talked about the collimator when we talked about cone cuts. What the collimator does is it restricts the size and shape of that primary beam. And the rule with that is that it has to restrict the size and shape of the beam so that when it comes in contact with the patient's face, it's no bigger than 2.75 inches in diameter. And that's for a dental X-ray unit. Obviously, that's going to be different if you're talking about a medical equipment unit that would be used for like chest X-rays and things like that. But in a dental X-ray unit, your collimator has to restrict and keep the size and shape of the beam to 2.75 inches in diameter or less. And that's the X-ray tube.